Jai Hind everyone. I am Navjyoti Sharma and Assistant Professor in Electrical and Electronics Department of Ajay Kumar Garg Engineering College. And today I am going to take in special topic of equivalent circuits and phasor diagram of a practical transformer, which is basically a topic which is covered in unit 3rd, that is magnetic circuits and transformers, of the subject basic electrical engineering, which is being taught in the first year according to AKTU syllabus. Okay, now coming on to the equivalent circuit of a practical transformer. Now, what do we understand, or what is the requirement for having an equivalent circuit of the transformer, or for studying the phasor diagram of the transformer, right? Now, as we see that we need to have the performance characteristics of the transformer. For that we require, generally in a transformer, what we used to have two circuits, right? The primary circuit and the secondary circuit, right? Which includes the primary winding, the no load component, right? The secondary circuit, the load component, right? But while having the performance analysis, likewise the efficiency of the transformer, or likewise the voltage regulation, in that separately we need not to consider the two circuits, right? So we can be having a single circuit so that the calculations are being simplified, right? For that we can always represent a transformer with its equivalent circuit, right? So the very first equivalent circuit what we are going to study is the exact equivalent circuit of the transformer, right? If at all I rectify this, this is exact equivalent circuit of the transformer. Exact equivalent circuit of the transformer. Exact, it is exactly the same way as the transformer is there. If you just see, this complete gives us the primary circuit, right? And this gives us the complete secondary circuit. As we see in the primary circuit, what are the components? The input voltage given to the transformer, that is being given by the voltage V1, right? The input current taken by the transformer, that is I1. R1, what is R1? R1 is the primary winding resistance, right? Primary winding resistance, that is being represented by R1. X1, what is this X1? X1 is the leakage reactance of the primary winding. As we have discussed in the earlier lectures also, what is this leakage reactance? Why we are representing it with a reactance X1? What used to happen in a transformer is, because of the leakage flux, the complete flux generated in the primary, that is not linking with the secondary. Similarly, the secondary flux which is being generated in the secondary winding, that doesn't link up with the primary because of the leakage flux, right? Because of this leakage flux, there used to be a drop in the induced EMF. How would we represent this drop, which is actually taking place because of this leakage flux? To represent this leakage, which is, or I must say, the drop which is occurring in the induced EMF because of this leakage flux, we used to introduce this leakage reactance X1 in the primary side as well and in the secondary side as well. So which gives me X1 as the primary leakage reactance and X2 as the secondary leakage reactance, right? So this is, up to this I must be saying this is the primary circuit. Then if at all we just remember that the input current to the transformer, that is I1, if we just see, this input current has to be the phasor sum of I0 and I2 dash. What is this I0? What is this I0? I0 is the no load current which is supposed to be flowing in the transformer at the no load condition, right? We have seen the no load condition of the transformer. When this load is not there in the transformer, then the transformer will not be deriving the current I1. In that case, this I1, the primary current taken by the transformer, will be just this I0, right? But when the transformer is being loaded, then the transformer will be taking a current I1, which is the phasor sum of this no load current plus the extra current taken by the transformer after the loading has happened. That current is being called as I2 dash. We'll be seeing what are the further relations. Just summing up, as we see, this is the primary current I1. It has to be the phasor sum of I0 and I2 dash. So I need to represent it with I0 and I2 dash, the two branches, right? Now, this I0, once again, this no load current, if you just see the no load circuit, this no load current is again the phasor sum of the two components of it. What are the two components? The magnetizing current and the working current, right? The two, magnetizing current. What is the function of the magnetizing current? To magnetize the core of the transformer, or to establish the flux in the core of the transformer. Similarly, what is IW? When the transformer is working and it is being loaded, at that time, it has to perform two functions. The input current has to perform two functions. What are the two functions? One is obviously to magnetize the core, to establish the flux in the core, right? Another one, it has to make over with the losses, right? Which losses? The losses which are taking place in the transformer. What are the losses taking place in the transformer? There are two losses. We know. What are the two losses in the transformer? One is the core loss. Another one, copper loss. What about core loss? These are the invariant losses, right? They are going to be present in the transformer at any load condition, let it be no load condition or heavily loaded condition, half load, full load, whatever, right? Whereas copper losses, these are current dependent losses, right? This is frequency dependent losses. Frequency of the transformer is remaining constant. That's why these losses are constant. Whereas copper losses, these are current dependent losses. And we are saying at no load condition, what is happening? No load condition, the I0 current. No load current, that used to be very small, right? This no load current used to be just 2 to 3% of the full load current. If that is so, this no load current is going to be very much small. Say, if the full load current of the transformer is say 5 ampere, right? The primary current of the transformer is say 5 ampere. At that condition, if at all I say if the rated load, if the rated current of the transformer is 5 ampere, what will be the no load current? Approximately 2 to 3% of it. So that means 0.1% or 0.01% or 0.01 ampere, right? That much small current and that much small losses which will be occurring because of this small current. I square R losses. At no load condition, it will be I0 square R losses, right? The resistance used to be very small as it is, and the current is also very small at no load condition. So the copper losses would be comparatively very much smaller and we can neglect them. So what I'll be saying that this working component IW is taking care of the complete core losses and a very negligible amount of copper losses which we may neglect, right? That's why this working component is also being called as core loss component, right? So coming back to the equivalent circuit, till now what we have discussed is, if the input voltage is V1, input current is I1, which is supposed to be the phasor sum of I0 and I2 dash. Once again, I0, which is nothing but the no load current, is once again the phasor sum of the two currents IW and IM, where IM is the magnetizing current, which is responsible for the magnetization or the excitation or for establishing the flux in the core of the transformer, right? that will be represented by an element X naught. This current would be flowing in the element X naught, which is represented as a reactance. Whereas the working component, which is taking care of the major core losses and a negligible amount of copper losses, which I may neglect, and I'll be just saying that this working component is just taking care of the core loss of the transformer, right? So that will be represented by a resistance. Next, I not this complete, if at all I just say, is the, if at all I just mark it, this is, I may be saying, is the no load circuit. This is the no load circuit. I2 dash, now coming to the another component of the input current, that is I2 dash. What is I2 dash? Now, if at all I say I2 dash, that is the extra current taken by the transformer when the transformer is being loaded. Initially, the transformer was taking only the current I0 when it is at no load condition. But when it is being loaded, because of the demagnetizing MMF being produced, the transformer will be producing its own further flux and also the current to overcome this demagnetizing MMF. While doing so, the transformer derives an extra current from the supply, which I used to call it as I2 dash, to make over with the load demand, required load demand, right? What is its relation? Why am I representing it with I2 dash? Certainly, it is having a relationship between I2. It is making over with the secondary load, the load which is being forced in the secondary side. So, it is having the relation, this I2 is equals to K times of I2, where K, what is K? K is the transformation ratio of the transformer. What is this transformation ratio? We must have studied. K is given by, it can be given by voltage ratio, V2 by V1. It can be given as turns ratio, N2 by N1. It can be given as the current ratio, I1 by I2, right? And if at all I say in phasor, this is in phase opposition to it. So, I2 dash is minus K times of I2. Okay. The one element which is remaining, that is the induced EMF in the primary winding. So, it will be represented by E1. So, this makes the complete primary circuit, right? So, the complete primary circuit, if at all we see, that is this. Right? So, this is the complete primary circuit of the transformer. Now, coming to the secondary circuit, right? Now, towards the secondary side of the transformer, the induced EMF would be E2. We know the relationship between E2 and E1. We have just seen they are related with the transformation ratio. Now, this secondary induced EMF E2 is driving our load, right, which is connected. I may be representing it with, say, ZL. What are the parameters involved in the secondary circuit? R2. What is R2? R2 is, it is the secondary winding resistance, right? It is the resistance of the secondary winding over here, represented by R2. X2, once again, we have discussed in the initial, X2 is the leakage reactance of the secondary circuit, right? V2, it is the terminal voltage which is occurring across the load. If we just see, this complete gives us the exact equivalent circuit of the transformer. Once again, how to remember logically, right? If we start with, how to start with the equivalent circuit of the transformer. We are having two circuits in a transformer, one is primary, secondary. The symbolic representation of a transformer, if we just see what is the symbolic representation of the transformer, that is the two windings, primary and secondary, being separated by a magnetic core, which is being represented by the two parallel lines. This side primary, the side to which you connect the load, that will be the secondary side, right? So if at all I see here, the load is being connected towards this side, so this is the secondary side and this is the primary side. So we have seen how to plot the parameters towards the primary side of the transformer, towards the secondary side of the transformer. So this is the exact equivalent circuit of the transformer. Now in this circuit, if at all, I want to give the relationship between this V1 and this E1. How can that be given? As we know that this no load circuit, this no load current is very much negligible, right? If that is so, I may be neglecting, for presently I may be neglecting this no load circuit. So what will be the relationship between this input voltage V1 and this E1? That can be very easily given just by applying our KVL, right? We know that, just to remember, this E1, this is the induced EMF, which is in phase opposition, or this is the induced EMF, and by the nature of every induced EMF, it has to oppose the very cause producing it. And what is the very cause producing it? The induced EMF that has been produced because of the alternating supply what you have given at the input. So this will be opposing the input voltage V1. So the expression what will be getting, or the relationship what will be getting for V1 and E1, it will be V1 must be equals to phasor, obviously, that will be equal to minus of E1 phasor plus, what are the drops we are having? Plus the drops. The drops what we are having over here is, if you just see, R1, X1, and the current flowing is I1. So the drops I am having is I1, R1 and I1, X1. So this is the equation which is relating the primary voltage and the primary induced EMF towards the primary side. Secondary, what is the relationship between the secondary induced EMF and the secondary terminal voltage? Once again, the KVL has to be used, and that can be given by, if you just see, now this time E2 must be equals to, the current flowing direction is this way. So this is positive, negative, positive, negative, positive, negative, positive, negative. So it has to be E2 is equals to the drops I2, R2 plus I2, X2 plus the terminal voltage V2. The phasor sum of all these will give me E2, right? So this is the equation which is relating the secondary induced EMF and the secondary terminal voltage. Just remember this, because this is going to be a very useful equations while we are drawing the phasor diagram of the transformer, right? This is all what we have discussed right now. Now this is again the equivalent circuit of the transformer, as we were discussing, that for calculation purpose, for analysis of the transformer, performance analysis of the transformer, the two circuits, analyzing two different circuits might be a tedious job. So what we can do, we can refer any one side of the transformer towards complete circuit towards one side, right? Either towards the primary or towards the secondary. Depending upon that, I may be having two types of equivalent circuit again. The first one is the equivalent circuit of the transformer referred to primary. Referred to primary. It means the primary circuit is as it is, fine. It is not going to get changed anyway. But what I am doing is the complete parameters which were there in the secondary circuit, here, the parameters which were there in the secondary circuit, those would be now referred towards primary side, right? I don't require now two different circuits. There will not be any two different circuits being electrically isolated, right? So this time I'll be drawing, although in transformer we will be having two different circuits electrically isolated, but when we are going for the equivalent circuit referred to primary, in that case will be just removing the coupling between the two and we'll be referring the secondary side towards primary side. Okay, if you just see here, now what are the changes in the circuit? We are going to start with the primary circuit as it is. The primary voltage V1, the primary current I1, which is once again the phasor sum of two, I0 and I2 dash, it is as it is. Primary resistance R1, leakage reactance of the primary X1, it is as it is. The no load circuit, if at all we see, this no load circuit is as it is. Once again, the no load circuit is having the two parameters, the working component, the two components, working component and the magnetizing current component. Magnetizing current flowing in the reactance X0, working current flowing in the resistance R0. Now, the mutual coupling between the two coils that has been removed, if you just see. So, I can say the induced EMF is E1, right? Now, I will refer one by one quantity from the secondary side towards the primary side, okay? So, the very first quantities R2. R2 was the resistance of the transformer in secondary winding. Now, when I am referring it towards the primary side, this value, the value of the secondary resistance has to be changed. So, that new resistance is going to be R2 dash, right? How much change? How much change it has to overcome, right? Anyhow, you know, we are now referring, we are drawing the complete circuit referred towards the primary, but the actual parameters of the transformer cannot change. That means the total copper losses which are dependent upon R1 and R2, they will not be changing. Even if I am referring it towards primary side or the secondary side, or let it be the exact equivalent circuit, the total copper loss of the transformer cannot change, right? If that is so, I have to take care that the value of the R2 dash, it has to be in such a way that the total copper losses of the transformer will not vary. For that, if at all we see, what is the formulation for the total copper losses of the transformer? The total copper losses of the transformer, that is given by I1 square R1 plus I2 square R2, right? Now, if at all I say we are referring the complete transformer parameters towards the primary side, that means the input current to the transformer is only I1. I am taking it outside. So, that is making me R1 plus right. So, I may again write it as I1 square R1 plus this I2 by I1, that gives me square, that gives me R2 by K square. So, I may further write it as I1 square R1 by R2 by K square. I am replacing it with R2 dash. Once again, combiningly these two resistance, I may call it as R1E. If you just remember, what is R1E? This is the equivalent resistance of the transformer referred towards primary. That is the total or equivalent resistance of the transformer when the complete resistance is being referred towards the primary side, right? So, I must be saying now the value of R2 has been changed to R2 dash, where the value of R2 dash is equals to R2 by K square. And what is K? K is the transformation ratio of the transformer given by V2 by V1, E2 by E1, I1 by I2 or N2 by N1, right? Okay, similarly, X2 dash, what is X2 dash? X2 dash is once again the referred value of the leakage reactance of the transformer secondary, right? When it has been referred towards the primary side, its value will once again be equals to X2 by K square. The thing what has happened with the resistance, right? Similarly, if at all I see the load impedance, that value was earlier ZL, but this time when you are referring it towards the primary side, its value will once again be ZL by K square. That means if at all you see over here, all the circuit constants what we are referring from the secondary side towards the primary side, they are getting divided by K square, right? R2 is R2 dash, which is equals to R2 by K square. X2 becomes X2 dash, whose value is equals to X2 by K square. Similarly, ZL becomes ZL by K square, ZL dash. Now, what are the further parameters which are getting transferred or referred? If you just see E2 was the secondary induced EMF, right? In the secondary winding, that has to be referred towards primary side. That will become E2 dash. Obviously, parallel, E2 dash would be equals to E1. And what will be its value? E2 by K. You'll be seeing that, right? We know the relationship between E2 by E1. E2 by E1 is equals to K. So, if at all I give, what is E1? That has to be E2 by K. Similarly, what are the next parameters which is remaining? This is V2 dash, the terminal voltage. V2 dash, that has to be equals to V2 by K. Now, let's check. Have we referred all the parameters of the secondary side towards the primary? Okay. So, we have referred R2 as R2 dash. We have referred X2 as X2 dash. We have referred ZL by ZL dash. We have referred E2 as E2 dash. We have referred V2 as V2 dash. One more, that is I2. I2, for I2 we are already having I2 dash, whose value is equals to K times of I2, that too minus, in phasor. Right, that itself is already there. We need not to just mention. So, I2 dash is equals to minus K times of I2. So, we have now the complete referring of the, we are now having the complete referring of the transformer, the secondary parameters of the transformer towards primary side. Now, coming to the next, that is the equivalent circuit of the transformer referred towards secondary side. Now, this time we are just going to do the opposite, right? This is the third equivalent circuit. In this case, now we are referring the complete primary of the transformer towards the secondary side. That means the secondary parameters are going to remain as it is. There is going to be no change in them. If you just see the secondary circuit, the secondary circuit, the load ZL, right? Terminal voltage V2, secondary resistance R2, secondary reactance X2, secondary induced EMF E2, secondary current I2. Up to here, everything is unchanged, right? So, what is the change? We are now referring the primary circuit towards the secondary. That means the parameters of the primary circuit are going to get changed. There will not be any mutual coupling between the two, right? So, we will not be having any two windings and being coupled by two parallel lines, right, or by the common magnetic core. So, if it will just see the input voltage, that is going to get changed as, initially we used to have it as V1, will be now be having its value as V1 dash. What is its relation? How it is going to get changed with respect to V1? So, if you just see V1 dash, it's parallel, it is almost equals to V2. V1 dash is equals to V2. And what is the relationship between V2 and V1? That is equals to V1 into K times, right? So, obviously, V1 dash is equals to V1 into K, right? Similarly, I1, the input current I1, that will be now referred, it will be a new value now, that is going to be I1 dash. What will be its value? Now, once again, my I1 dash, this no load current is very small. I1 dash is very much equivalent to I2, or I may say just equals to I2. And what is its relationship? I know it has to be I1 by K according to the transformation ratio. So, I1 dash is equals to I1 by K. Once again, the no load current I0, that will be I0 dash. So, I am writing it over here. I0 dash will now be I0 by K. Similarly, its working component IW dash will be IW by K. IM dash, that will be IM by K. Circuit constants. Now coming to, these are all currents and voltages what we have done. Coming to circuits constant, likewise, R1 will now be changed to R1 dash. Once again, its value will be changed in such a way that the total copper losses of the transformer should not get changed, right? That can be once again taken care of. Likewise, we can see over here, total copper losses of the transformer, that can be given by I1 square R1 plus I2 square R2. If now this condition is being considered, referred towards secondary side. So obviously, the current which is flowing is say I2 square. I'll be taking that as common. I1 square R1 plus R2. What is I1 by I2? That is K square. So that becomes K square R1 plus R2, which is I2 square R2E. What is R2E? This is the equivalent circuit of the transformer referred towards secondary, right? Prior to that, the value of the R2 has been changed to K square R1. The value has been changed to K square R1. So, if you just see here, the value of R1 dash can be given as K square R1. Similarly, X1 dash, the leakage reactance, that will be given by K square X1, right? R0 dash, that can be given by K square R0. X0 dash, that will be given by K square X0. So, we have covered all the parameters of the primary side and has referred towards secondary. One is remaining, that is I1. The I1 will be referred towards secondary. Its value would be equals to E1 dash. E1 dash is almost equals to E2. So, its value is going to be E1 into K times, as we have found for V1 dash. So, this is the equivalent circuit of the transformer referred towards secondary. Now, coming to equivalent circuit of the transformer, we have seen three equivalent circuits. One was the exact equivalent circuit of the transformer, where we have considered the two circuits separately, primary circuit separately and secondary circuit, right? Then equivalent circuit of the transformer referred towards primary side, where the secondary parameters were being referred towards the primary side. Then the equivalent circuit of the transformer referred towards secondary, where the primary parameters of the transformer has been referred towards secondary side. Now is the approximate equivalent circuit of the transformer referred towards primary side. In this, what we have done, this is approximation we have done, because in case of earlier, if you just see the equivalent circuit of the transformer referred towards primary side, here I am having R1 and X1, the primary resistance and reactance, secondary resistance and reactance referred towards primary side, but the currents flowing in both of these are different. So, if at all I want to combine them to have the equivalent resistance of the transformer, that becomes a tricky situation, right? Although I1 and I2 dash are very much same, right, because the no load current is very much negligible. But even then, when we are going for the equivalent circuit of the transformer, we need to have them on the same side. For that, what we used to do, we used to create a deliberate error, and we used to shift the no load circuit towards this side, right, and make our R1 and X1 to be present on the another side, right, so that this time I can be combining R1 and R2 dash. Combiningly, R1 and R2 dash is going to get me R1E. What is R1E? This is the equivalent resistance of the transformer referred toward primary side. Similarly, X1 and X2 dash is going to get me X2E, that is equivalent leakage reactance of the transformer referred towards secondary side, right? In that case, I am getting the equivalent resistance referred to primary and reactance, X1E, equivalent reactance referred towards the primary side. Combiningly, these two I am getting, if you just see, I am getting the R01 or what R1E and X1E. Combiningly, these two I will be getting Z1E, that is equivalent impedance of the transformer referred towards primary, right? So this is the simplified equivalent circuit of the transformer referred towards primary, where the primary circuit is as it is. We have shifted the no load circuit prior to R1 and X1 so that the R1 and X1 can be combined to R2 and X2 dash, so that the equivalent impedance of the transformer can be derived. Now this is all regarding the equivalent circuit of the transformer. Now coming to the phasor diagram of the practical transformer. Now the phasor diagram of the practical transformer is in fact once again required for the performance characteristics, and that will be derived from the equivalent circuit as it is, right? So coming to the resistive, because now this is a practical transformer being loaded, so the loading conditions is also very important, right? It plays an important role. Which kind of load is connected towards the secondary side of the transformer? The load can be of three types. We have seen what are the three types of loads we can be having. It can be either resistive load, it can be inductive, it can be capacitive. So going for the resistive load first of all, right? If the load is resistive, if the load is resistive in the transformer, so what will be the relationship between the secondary voltage and secondary current? I'll be just drawing the equivalent circuit of the transformer without considering the no load circuit, right? So if at all I just say this is R1, X1, this is R1, X1, the input current I1, voltage V1, E1 is the induced EMF, E2 is the secondary induced EMF, I2, R2, X2, the load being connected, and V2 is the terminal voltage. So what we are saying over here is, if this load what we are considering, if this load is purely resistive, right? In that case, obviously, the voltage across the load, that is V2, and the current flowing through the load, that is I2, they will be in same phase, right? So one of the things we have to remember is this, that V2 and I2 will be in same phase for a purely resistive load. Secondly, we need to remember the two equations what we have given for the primary voltage, the relationship between the input voltage V1 is equals to minus of E1 plus I1 R1 plus I1 X1, and the secondary E2 is equals to V2 plus I2 R2 plus I2 X2, right? Now, starting with the reference, which quantity has to be taken as reference. The quantity which will be taking as reference has to be the flux, right? Why? Because this is the quantity which is common to both the primary and the secondary circuit. So we'll be considering I naught as flux as our reference phasor. Then we'll be plotting the no load current. This no load current magnitude used to be very small, right? The no load current I naught. Then we know that the induced EMF in the primary, that will be lagging the flux from the derivatives, if at all I go. So E1 will be lagging the flux by 90 degrees. So I'll be plotting E1 90 degree lagging the flux, right? I also know that if E1 is over here, the anti of that would be, if E1 is over here, the anti of that would be minus of E1. So I have one phasor that is minus of E1. Next, to have I1 R1 phasor to be plotted, what is this I1 R1? I1 R1 is a purely resistive voltage. If this is a purely resistive voltage, the voltage and the current, which current? The corresponding current, which is I1, that has to be in same phase, right? So what is the phase of I1? So first I need to know what is the phase of I1. That means I need to plot I1. For plotting I1, I have to go with the basics, that I1 is the phase sum of I naught and I2 dash. I naught I have plotted arbitrarily, fine. But what about I2 dash? Now once again, I2 dash is minus of k times of I2. Say k is 1 for me, right? Assuming. So it has to be minus of I2. Once again, if I2 has to be seen, I have to see the kind of load. If at all I have to see the kind of load being connected. So, the kind of load is purely resistive. If that is so, V2 and I2 would be in same phase. So, arbitrarily in the third quadrant, I'll be drawing V2 and I'll be making sure that I2 is in same phase. Right? If I2 is over here, what will be minus of the I2? Minus of I2 has to be in opposite side, that is I2 dash. Now, the phasor sum of I0 and I2 dash is giving me I1. Now I know what is the phase of I1. If that is so, I can plot the phasor I1 R1, right? I1 R1 purely resistive voltage, it has to be in same phase with I1. So what I'll be doing, I'll be adding a phasor I1 R1 in such a way that it is in phase with I1. That means just parallel to this I1. I1 is over here. In parallel to this, I'll be drawing a phasor I1 R1. We know that two parallel lines in a phase, both of them are in same phase, right? So I'll be having I1 R1. Now next is I1 X1, right? That is a purely inductive voltage. It has to lead the current by 90 degree, or the current has to lag the voltage by 90 degree. So I'll be drawing a phasor leading the current by 90 degree, right? I'll be just now putting up the final phasor. Obviously, this final phasor has to be V1. Now it can be seen very easily that V1 is equals to minus of E1 plus I1 R1 plus I1 X1. Similarly, the secondary circuit. The primary circuit is over now. Coming to the secondary circuit, E2 must be equals to V2 plus I2 R2 plus I2 X2. If that is so, I am already having V2. V2 is being already plotted. Now I require I2 R2. I2 R2, it has to be in same phase with I2, right? So I'll be extending the same phase, I2 R2. Now, I2 X2, that is once again a reactive voltage, right? Has to be leading by 90 degrees. So I'll be drawing it towards this side with an angle of 90. Now what will be this complete phasor? This complete phasor would be E2. It can be now very easily justified that E2 is equals to V2. This is V2 plus I2 R2 plus I2 X2. Okay. Now coming to the other kind of load, that is another kind of load, that is inductive load, right? Now in case of inductive load, the basic equations what we were considering between the input voltage and the induced EMF, the secondary induced EMF and the load voltage, that is going to remain same, right? The only thing which is going to vary is the performance between the V2 and I2, because the load is now being inductive. It is not purely inductive, it is an RL circuit. So if that is the case, the current will lag the voltage by 90 degree by certain angle phi. Which current? The secondary current. I2 will lag the voltage V2 by a certain angle phi 2, right? So once again, we'll be starting with the same reference, that is flux, which is common to both primary and secondary winding, right? The no load current, I0, the primary induced voltage which will be lagging the flux by 90 degree, E1. Just in opposition to the E1, we'll be having once again minus of E1. We have seen this in the earlier one also, right? Once again, for having I1 R1, I need once again I1. What is I1? That is once again the phasor sum of I0 and I2 dash, right? I0, the no load current being plotted arbitrarily, and then I2 dash. For I2 dash, this time we require the nature this time of the load is inductive. That means the current would be lagging the voltage by certain angle phi 2. If this is I2, we have shown just in opposition to that will be I2 dash. I0 is over here. So now the phasor sum of these two will give me I1. Now once again, the phase of I1 is known to me. If this is the phase of I1, then once again I1 R1 can be plotted just in phase with it. So the two parallel lines having the same phase. So I'll be drawing a line, a phasor I1 R1 just in parallel to I1, right? Then I1 X1, once again purely inductive voltage, it has to be leading in nature with reference to the current, right? So I1 X1 is the leading voltage. Now once again minus of E1 plus I1 R1 plus I1 X1 will give me V1. The primary circuit is done. Once again coming to secondary, what was the relation? E2 is equals to V2 plus I2R2 plus I2X2. V2 is already there, we have already plotted V2. Then I2R2, it has to be in same phase as that of I2. So just extend this line. So I'll be drawing a line which is in just phase with I2, a parallel line to I2. Then in 90 degree, I'll be having I2X2. This complete phasor will then be E2. Similarly, the third kind of load can be covered. So the last topic, that is the phasor diagram of the practical transformer with capacitive load. Now this time, what is the change? The change is once again the load, right? If that is so, the relationship between V2 and I2, only this parameter is going to get changed. This time, because this is a capacitive load, the current I2 will lead the voltage by certain angle phi 2. If you just see here, this I2 which we have shown in the third quadrant, that will be leading the voltage by certain angle phi 2. Rest of the parameters are going to remain same. In a brief, I am going to cover it up. Once again, the reference phasor phi, lagging to which by 90 degree I am having induced EMF E1. The no load current which is being shown arbitrarily as I0 with the two components IM and IW. Then if this is E1, in phase opposition to it, I will be having minus of E1. If I2 is over here, which we have plotted in the third quadrant arbitrarily, then if I2 is here, in opposition to it, I will be having I2 dash. The phasor sum of I0 and I2 dash is going to get me I1, right? I1 phasor is now achieved. If that is so, I1 R1 can be plotted now, just in parallel to I1. If that is so, I1 X1 90 degree to it, and finally V1, the resultant phasor. Secondary circuit, V2 is already with us. Then I2R2 which has to be in same phase as that of I2. So I am just extending I2 and drawing a phasor which is in parallel with I2. And then I2X2, leading it by 90 degree, and final phasor, that is E2. It has to be in same phase with E1, right? So here we comes to the end of the topic, equivalent circuit and phasor diagram of the transformer. Thank you.